Hi everyone, welcome to Data 605 final exam presentation. Data 605 is a lecture on computational mathematics. Shout out to Professor Lawrence for all the excellent support. This presentation is broken down into three sections: probability, statistics and calculus, and modeling. I've loaded all the necessary libraries for use in this presentation. The first section is broken down into random number generation and probability. Under the random number generation, we assign random variables to x and y, which is random uniform numbers and random normal numbers, respectively. We then print out to just confirm that we have the right numbers right there. Jump to probability. Here we assign small letter x and small letter y to be the median of variable x and the first quartile of variable y, respectively. We then proceed to do some calculations on probability. First one is the probability of x being higher than its median, given that x is greater than small letter y, which is the first quartile of y. From the calculation, we get 54% as the result. I proceed to do the same for section B and section C, obtaining 37 and 45%, respectively, being the result for these two solutions, or rather equations. Next is to investigate whether this equation holds. Here, the first step is to build a table and to evaluate marginal adjoint probabilities. As you can see, the results are the same, meaning that our equation is true. Next, we want to use Fisher's exact test and chi-square test to confirm whether our independence, or rather that equation, holds. And from these, the results we obtain conclude that this is true. We have a large p-value in both cases, actually almost exact same p-value for both of them. Just note that the chi-square test applies to approximations, while the Fisher's exact test runs an exact procedure, of course, for small size samples. We jump to problem number 2. Here, we load data from kaggle.com and select 3 features, which we'll use for upcoming analytics. First, we do some descriptive statistics on lot area. We use both summary and descript functions in RStudio for these analytics. Of course, there are about 1,460 observations for all the variables, for all the 3 variables. For lot area, we see it's right skewed and has quite a number of outliers. Sales price, same number of observations, again skewed to the right as well, with a number of observable outliers. Same statistic on garage area, using summary and descript functions. Again, 1,460 observations, skewed to the right with a few observable outliers. I brought a scatter plot matrix for these variables, both the dependent and the independent. And to some extent, there's some correlation between sale price and garage. There's not any notable correlation between lot area and the sale price. And this is expected. Of course, if you look at the conclusion, a large garage would mean a large house, which to some extent would mean a much higher price. The lot area, uh, again, a large lot area does not necessarily mean a large house. Could be a small house. I derive a correlation matrix for the three variables again, and this confirms the observation from the graphs in the previous slide. Of course, same conclusion right here. Here, I test the hypothesis that the correlation between each pairwise set of variables is zero at an 80% confidence interval. Of course, it's not zero. We have some correlation between them with varying degree. Of course, there's a high or a strong correlation between garage and sales price, and a weak correlation between lot area and the sale price. I want to address one of the questions here about family-wise errors. Unless we review all the variables, which might have an impact on the correlation, then it's possible we are likely to reject true null hypothesis. And yes, I would be worried about family-wise errors. Next, we jump to linear algebra and correlation. Using the correlation matrix from the previous section, we invert it using the solve matrix to obtain the precision matrix. We proceed to multiply the correlation and precision matrix and the precision matrix with the correlation matrix. We obtain identity matrix. This is expected. We decompose the two matrices, the correlation matrix and the precision matrix, to obtain the lower and the upper triangular matrices. We then multiply the upper and the lower triangular matrices for these two matrices, the correlation matrix and the precision matrix. And what we get is the original matrices. This is within our expectation. We jump to calculus-based probability and statistics. We select the garage area for these analytics. We check to see the minimum, which is actually 0, but we choose, or I choose not to shift it, since houses with no garage should have an area of 0. Again, a histogram right there to visualize this. Here, we want to fit an exponential probability density function to our data. And again, we also want to generate about 10,000 samples from this exponential distribution. So we obtain an optimal value for lambda, which is about 0.002114. And we assign these 10,000 samples to SUMP, in this case. We plot histograms to evaluate the observed and simulated data. Of course, from the conclusion, the simulated data is more heavily skewed to the right, while the observed data is more concentrated to the center. We proceed to compute the 5th and 95th percentiles of the simulated data. These are the results. We then generate 95% confidence interval, which then lies between 467 and about 477. Assuming normality, we plot a histogram right here, and then proceed to compute the empirical 5th percentile and 5th percentile of this data. Of course, the results are within expectation. 5% around 0, and 95% around 850. We proceed to modeling. Here, we load training data. On loading this data, we want to evaluate and eliminate some of the variables that are not of any much use to us. An example would be those with limited features or missing data. On elimination, we load the selected features. We then uh, eliminate any NAs from the data, and we feed these to an initial model. We then generate the model statistics to see how well the model is likely to perform. Multiple R squared of about 88%, which is great. So from here, we are not going to do to make any more changes to the model, and we are going to proceed to test. Under test, we load test data from the website. We then feed this data to our model and produce the output. This output will be uploaded to the competition website on kaggle.com, and from there we'll see the kind of results we manage. As you can see, the model managed to obtain a score of 2.50090, which is not very impressive. But I later used Python and obtained a score of 0.31772, which was a huge improvement from the initial model generation. The Python code is saved under my GitHub right here, as well as the R code for this presentation. Thank you, and feel free to leave your comments and provide any feedback. Thanks.